Okay, I'd like to now turn our attention to a quantity called momentum, which we'll find that in many circumstances is a conserved quantity, meaning that it's the same both before and after a process. So the definition of momentum that we'll be using here, and I will give a caveat in just a second. Newton's definition of momentum is that it is the product of an object's mass and its velocity. So this is a scalar times a vector, which will give us a vector quantity. And I have no clue why it is that the symbol for momentum is P, other than just it's close to the letter M in the alphabet, and M was already taken from mass. Now, since masses are always positive, it will always be the case that momentum and velocity will point in the same direction. Although when you're drawing them, it doesn't matter how much longer, say, you make the momentum vector than the velocity vector, or even make it shorter, because after all, the units of velocity are meters per second, but the units of momentum are kilogram meters per second. And so it's meaningless to compare these two lengths since the lengths represent different units. Now, one of the funny things with momentum here is that although it's proportional velocity, since the mass also comes into play, you can have the momentum of two things be the same, where one thing is something lightweight going fast and something else is fairly heavy but going slow. For instance, we could imagine having a tenth of a kilogram mass here, and having it move at a velocity of 100 meters per second to the right. The momentum will also be pointing to the right, and that's going to be equal to the mass times the velocity. So the magnitude would be 0.1 kilograms times 100 meters per second, gives us a momentum of 10 kilogram meters per second to the right. By the same token, I could say have 1,000 kilogram mass, barely moving. Moving at a centimeter per second, 0.01 meters per second. And the momentum of that object would be exactly the same as the first object, because the magnitude of the momentum will be the mass times the velocity. So that will be 1,000 kilograms times 0.01 meters per second. Gives us 10 kilogram meters per second. So it isn't just how fast something's going or how massive something is, it's the combination of the two. Now with that defined, I meant to give a caveat. It turns out that with the discovery with the development of Einstein's theory of special relativity, that we have had to modify the definition of momentum somewhat. So the current definition is actually that it is mv over the square root of 1 minus v squared over c squared, where c is the speed of light, which is just a shade under 3 times 10 to the 8 meters per second. Now, unless something is moving absurdly fast, this correction factor in the denominator doesn't show up at all to any number of significant figures you would care about. For any everyday life kind of thing, m times v is just fine. But I just want to put that there so that later when you go and learn about special relativity in electricity and magnetism, you'll see that this is the actual current accepted definition, and we're using Newton's original definition because to all the significant figures we'll ever care about in daily life, it's fine and it's easier to use. Now, you may or may not remember, but when we were going over Newton's laws of motion, I pointed out at the time that it wasn't really correct to write F net equals ma. Instead, if you followed what Newton actually wrote and put into mathematical symbols, so this is the correct form of Newton's second law, and it's still correct even under relativity, is F net equals dp dt. So this is where the the net force on something is equal to the time rate of change of the momentum. Now, I mentioned at the time that if the mass is a constant, that this amounted to F equals ma. And we can see this by just literally going ahead and differentiating here. So we'll say F net equals dp dt. So this is d dt of m times v. But if we say that m is a constant, then that's m times dv dt. But oh hey, v is the acceleration. dv dt is the acceleration. So we get F net equals ma. So as long as the mass is a constant, we can go ahead and write F net equals ma. Or we also have the other caveat that we have to be moving slow compared to the speed of light, but 3 times 10 to the 8 meters per second is so fast that even the fastest things happening on Earth are a very small number compared to that, and then you're going to square it, and so it just really doesn't matter for daily life. So now with that, let's go ahead and define impulse. So, impulse. So the symbol for impulse is a capital J. And in this case, the reason why it's a J may seem a little weirder than you would think. It's not just because it's right next to the letter I, and capital I gets used for moment of inertia, which shows up more often. But it's also the case that only in the last couple of centuries have people really started to think of the letters I and J as truly being distinct. And so at the time when people were first starting to think about this, J was just sort of seen as another way of writing the letter I. So there you go. Anyway, it is defined as the integral with respect to time of the force acting on something. And keep in mind, since I'm a physicist, I usually like to stick what I'm integrating over next to the integral sign. And this is going to be a definite integral, so this will be from t initial to t final. Okay, so this is a vector equation. So this means if you want, say, the x component of it, this would be the integral from t initial to t final dt of the x component of the force, and so forth. Our units of impulse are going to be newtons times seconds. We'll see that this has the same physical dimension as momentum, kilogram meters per second, but we usually write as newton seconds just so we know that we're talking about impulse. So again, as always here, I'm not going to go too crazy with asking people to integrate things in this treatment. But just remember that whenever we see a definite integral, what that means is if I plot, say, the x component of force against the time, like so, that means that this area under the curve right here with the usual caveats that if we go below the t-axis, the area is counted as negative, is in this case the x component of the impulse. And like I had mentioned, this has, not coincidentally, the same unit, the same physical dimension as momentum. So let's just check that out right now. A Newton times a second. A Newton is a kilogram meter per second squared. If I times that by seconds, I have kilogram meters per second. So it has the same physical dimension as momentum, and you would suspect that since I introduced these two right next to each other, that probably they are somehow related, and you would be correct. They are related through what's called the Impulse-Momentum Theorem. So Theorem. There we go. So we'll start with the correct version, with Newton's version, Newton's second law. Again, we're not going to worry about the relativistic extensions here, and we'll say F net equals dp dt. Dp dt. I can rewrite this as dp equals F net dt. And then what I can do is I can go ahead and integrate both sides. I would integrate here from the initial to the final. Sorry, P initial to P final, like that. And from here, I would integrate from T initial to T final. Well, this bit right here is just the impulse that we saw before. This bit right here, if I do this integral, it is going to just be P final minus P initial. This is the impulse. Hey, that's the change in momentum. So we can write this as the impulse exerted on something will be equal to the change in the momentum that that thing experiences. Now, the reason why we don't make a huge deal about impulse for the most part is that we will be mostly looking at situations, well, mostly trying to bend over backwards to find situations where the impulse is zero. We'll try to define the system to make that happen. And by doing that, we'll be saying that the change in momentum is zero, meaning that P final equals P initial, or momentum is conserved for that situation. That'll be the focus of future videos. There is, however, one sort of useful practical thing, and that is trying to characterize average forces for what I like to call hammer hit kind of situations. So these are rapid transient forces. Like for instance here, so the idea goes like this. Real world things like, say, striking a hammer against a nail, things like that, tend to happen over a period of about 20 milliseconds-ish. And there's a lot of wiggle room in that ish part, but less than or on the order of 20 milliseconds from, say, when a hammer first strikes the nail to when it finishes, when the nail has left the hammer. And the force goes up rapidly and back down rapidly over this, not 20 meters per second. What am I doing here? 20 milliseconds. So 20 thousandths of a second. So a lot of times it's very hard to get a clue of what the maximum force might be. In a engineering lab bench kind of situation, test bench kind of situation, it's often fairly straightforward, though, to measure how much the momentum of the thing changed. And you can use high-speed photography to figure out how long it was in contact to get this time delta t right here. So this gives us a way to characterize an average force. And what you can do is say that the average force that gets exerted over this time is just the one that gives the same impulse. Like so. So we'll say that this is the average force. And then what we do is we just demand that these impulses, these areas under the curve, be equal. So this is just a definition of F average. But what this lets us do is say let's say we took a look at some sort of situation and we found that the change in the momentum was 0.1 kilogram meters per second. What we could do with something in this case here is we can say, well, the impulse would be equal to F average times our contact time. F average delta t. Like I said, we can figure out the contact time from high-speed videotape or video recording or something like that. And this would be equal to delta p, which was something that we could measure. So we can say, well, then F average would be equal to delta p over delta t. So in this case, it would be 0.1 kilogram meters per second over 0.02 seconds. Well, that's going to give us 5 newtons. Now, that is not giving us the maximum force, but say if we were trying to design a nail that was going to be struck by such a hammer, what you might do is say, well, I can't conceive that this maximum force is ever more than 10 or 20 times or something like that, what this F average is. And then you just go ahead and design around whatever wiggle factor you want to give to relate your best guess of F max to F average. Obviously, the more critical the system is, the more conservatively you would design it. At least gives you a starting point before you start building things and breaking them in test rigs. So that can save you a little bit of money there. All right, so in the next video, we will go ahead and take a look at what are called isolated systems, where, like I was alluding to earlier, the momentum before and after the collision is the same, and we'll see what that means. So we'll catch you over there.